I gave up on protein shake. I hate them.
You know, if you work out, it turns a whole lot bad.
Yeah.
So it's like really bad. Unless you work out.
No, yeah. I drink them in like midday and then usually at like 5. But yeah, that's why I'm a little bit.
All right, guys. Let's get back in it. Oh, damn it, Jeff. You just stayed out of here for a little while. All right. So let me just ask you this question: If there's a piece of my formula, if there was something, let's just be very specific. If I don't know what this really is, what do I have to use instead? What is this? Standard deviation of the population. It's Greek letter, right? So that's the mu and the sigma are for population. So if I don't know what sigma is, what do I use instead? What's this? What's this? Sample mean, right? Why am I using a sample mean here? Because I didn't know what the population mean was. If I don't know what this population standard deviation is, what am I going to use? Sample standard deviation. I took a sample, didn't I? Took a sample size n to get x bar. So can't I also get s? In fact, in the book, there will be problems where you know both sigma and s. If I know both sigma and s, which one do I use? Frickin' sigma. Holy shit, that's the real standard deviation. I only use s or x bar when I don't know mu or sigma. Are you guys semi with me? Those are my best guesses for what they are. So if I don't know, holy shit. If I don't, where's my blue marker? There you are. If I don't know sigma, two things. One, use s instead. Yeah, I always want this. I really want this to make sense. What do you think I have to do if I'm using an approximation for sigma? What should happen to my confidence interval for any one I make? I'm not as sure as I was about a piece of it, so my confidence interval should have to do what to make up for that? You could do this. So, all right, let me go back to my fish analogy. No, not changing the sample size or anything. So let's say I know that there's a fish in this pond, and I know the standard deviation of how much it moves away from its home. Are you guys with me? It's got a little place it calls home. Aw. Waiting for Nemo to come back. Oh, or Dora. I forgot. And so I know how far it gets away from its home. So I kind of know how big of a net to throw out to be such and so confident that I catch it. Are you guys semi with me? Can you see that? What if I wasn't as sure about how far it gets away from its house? Am I going to throw out a bigger net or a smaller net? Bigger frickin' net. If there is a piece of this that I'm not sure about, for example, the sigma, if I use an approximation instead, I somehow have to make my confidence interval bigger, cover my ass more, right? Use a bigger towel. You guys with me? A little bit. Does that just make sense by itself? Please, you're good. Second thing is, when am I more sure about this being close to this? When am I going to be more sure about what I see in a sample when the sample itself is, now you can say this, when the sample size is bigger, then I'm more sure. Then I need less and less. I don't need as much of a net. I don't need as much of a towel. Cover my ass. Maybe. So. I really want this to make sense. If I took a big ass sample, if my sample was huge, then I can basically say the SIC is sigma. If I take almost the whole population, then I'm like, it's got to be really close to what the real sigma is. Holy shit. So the bigger my sample gets, the closer my wider confidence interval can get to what it normally would be. So here's what we do. If I don't know sigma, if I only know S, and of course it's normally distributed, I need to be to be able to do anything. I use what, so let's say this. If it's normal, and I only know sigma, only know S, we will use a score that is bigger than Z score. It's always going to be a little bigger than the Z score, and it gets bigger when the sample is really small, and it gets smaller and closer to a Z score when the sample gets bigger and bigger and bigger. So let me give you this chart. We're only going to have one more chart after this one. So you got your Z-scored chart. This one is called a T-scored chart. And here's the story real quick. Just in case this interests any of you. But the person that came up with the T-score distribution, he worked at the Guinness Brewery. And the work he did, since he worked at the brewery, any analysis he did belonged to Guinness. So he submitted his work under a pseudonym. He called it Student. He called himself Student. So he had to pretend he had to be anonymous, or else the Guinness Brewery would have owned his work. So this is very often called the Student's Tea distribution. His name was William Gossett. Worked at the Guinness Brewery. I don't know if anybody likes Guinness. So I always say that just in case that brings somebody more into this. That's the truth. I mean, this guy. So let's look at this. Yes? Oh, okay. I love this. You ready? So one thing to realize, let me build up to that in a minute, okay? Degrees of freedom. You guys, anybody remember that? No, so degrees of freedom. Does anybody remember what that was? That came up when we first did standard deviation for a sample. I had to divide not by n, I divided by n minus 1. That was the degrees of freedom, right? Why was it n minus 1? Because I can make up n minus 1 things, but then the last thing has to be something specific to make the whole thing have a mean of something. So it's related to how much freedom I have in a list of numbers. How many numbers can I just make up, and the last number is the one that saves my ass to make the mean come out to be something. It's related to that idea. That's why we call it degrees of freedom. It's n minus 1. Okay, you guys with me so far? So that's this column here. So if I had n of 17, where would I go? N is 17. I would go to 16. And then look this way and figure out what the hell. All right, so the next step is going to be that. How the hell do I tell which thing to look at? So first thing I want to tell you and ask you is, when you make a confidence interval, can somebody tell me how many tails do you make? So if I was going to draw a confidence interval in here, it would be like this maybe, right? How many tails did I just make? 2. So if I want to make like a 99% confidence interval, what percentage is in 2 tails? What percentage is in both tails altogether? 1%. And here's the symbol for that. Here's the symbol. This is kind of nice. The symbol for the amount of area that's in the tail or tails is a little fish dude. It's the Greek letter alpha. Little fish dude has a little tail. So this, if I say alpha equals 0.01, bless you, that means there's 1% in the tails. So look how you almost can't go wrong. How much is in just this one tail then? So So if I cut this in half, I get 0.005. Now look at the chart. If I got 0.01 in two tails, and we just said you got 0.005 in one tail, see how you're in the same freaking column? You can't go wrong. If you cut it in half, just make sure you look at the one tail. Now, look at the very bottom where it says large. Does anything there look familiar at all? These numbers that are next to where it says large, what are some of them looking like? Z-scores. 11. Sorry, I cut you off there, man. I knew you were going to say it. Right? 1.645. That sounds very... 1.96, we just did one with 1.96. And then 2.33 with 2.326, be a little more precise, and all this other shit. So those are Z-scores. And what did I just say? When do I not need my ass covered anymore is when my sample is large. And I love that they can't answer your question specifically because it depends on the situation. What is large? Depends. Totally depends. Some of these charts say large is above 50. But do you see how it's still changing by quite a bit? But notice, do you see how it's by a step of 1 up here? And then it's by a step of 5, 10, hundreds, thousands. Because the bigger my sample gets, the closer the standard deviation gets to the right answer. If I take a really small sample, my S could be like crazy off. But if I take a huge sample, then my S is going to be really close to something, but I don't need to make my confidence interval that much bigger. So I really want this. So we just did a 95% confidence interval, that last problem we did, right? And if 95% confidence, how much would be in both tails? In two tails, there would be 5%. So that would mean I would look here. If I go all the way to the bottom of this, I get a Z-score. That's the trick. You could use the T-score chart to get Z-scores. If you stop, you get a T-score. If you go all the way to the bottom, you get a Z-score. Now, what if we had done that same problem? I don't remember what N was. What if we had done that same problem, but I didn't know sigma? And N was 32. What would I have used instead of 1.96? I would have used 2.040. So when I don't know sigma, I can't use the Z-score. I've got to use a score that's a little bigger. Because what does that do then? It makes my confidence interval bigger to cover me for this unknown piece. So if there's something you're not sure about, don't you have to be conservative? When's the cable guy going to be here? He said anywhere from 8 to 8. Oh, shit. All right. I'm really not sure when he's going to be there, so I got to cover the whole day. You guys with me? Whereas if they said 11 to 1, which they would never say, then you're like, oh, I just need a lunch break that's really long, and I can cover it. I don't have to cover it. I'm more sure about when they're going to be there. So the smaller my sample is, and I only know S, the bigger my confidence interval has to get. That's why these scores get bigger and bigger and bigger as you go up. Because it's smaller and smaller samples, you're less and less sure, your confidence interval's got to get bigger to cover your ass for that. All right. I don't know how many more ways to say that, so I'm going to stop saying it.
So the values that we get here, this would be the Z-score?
T-score. So here's the formula. Ready? This formula kicks so much ass. You're not allowed to have notes on your formula sheet, right? Formulas are notes, though. So what are you going to have in the little section on your formula sheet for confidence intervals? You're going to have this guy. You're going to have this guy. And then right in between, in the middle, you're going to have, count me. Instead of Z, if I only know S, I can't use a Z-score, you have to use a T-score. So you're going to have that formula sitting there. So if you're on the test, you're like, when do I use T-score again? The formula says, dude, you use T-score when you only know S. It says it. When am I allowed to use a Z-score? When into the population standard deviation. When do I have to use a T-score? When I only know S. Now what's got to be true about both of them? What tells me I can do anything? The distribution is normal. Somebody had a question. You're good? Okay. All right, so.
What does S stand for?
Oh shit. It doesn't stand for shit, sorry. What is S? Sample standard deviation. All right, so on the back of that sheet we just did, you turn this bad boy over, you'll see this. So let's see. So look at that first one. If n is 6, what's the degrees of freedom? Oh, 5. Which column am I looking at? So I know I'm going to go to 5. Get this over here. Which column am I going to look at? I want to be how confident? 99% confident. So what's alpha then? 0.01. And I want to stop at 5. Sorry?
5.
N is 6. Degrees of freedom is always n minus 1. Is that cool?
Yeah.
So I'm going to go to 5. I'm going to stop there, and I'm going to use that score. 4.032. That's huge, because a sample of 6 is nothing. So it's got to really cover my ass. Big time. Keep going. Try to do this whole page. You can do it. You can work with other people if you want to.